There are precise mathematical definitions for the terms linear, constant, quadratic, and so on. And these definitions are useful because they allow you to prove properties of functions without ever running those functions on particular examples. And one important component of the theory of computing is this practice of proving characteristics about functions by reasoning from mathematical definitions. Now, that's not a topic in this course, but it is covered extensively in future courses at Berkeley, and it's a standard part of the computer science curriculum. Rather than telling you all the definitions, which you're welcome to look up on your own, I will show you the standard notation that's associated with those definitions because it's used so commonly that it might surprise you if you've never seen it before. So for these common orders of growth, exponential, quadratic, linear, logarithmic, and constant, the most typical way to describe each order of growth is with either big theta or big O notation. Big theta notation looks like this, and there's a different expression for each order of growth. So quadratic growth is big theta of n squared, whereas linear growth is big theta of n. And yes, computer scientists really do wander around saying big theta. Logarithmic is log n, and constant is the tricky one. You write big theta of 1 most commonly. And what happened to the n? Well, increasing n doesn't affect time in a constant growth function, and so you don't put n there at all. Another common set of notation is big O notation, which is even more fun to say than big theta. And the expressions look the same. So big theta of b to the n or big O of b to the n. Now, these actually mean something slightly different. Big O describes the upper bound for the time it takes for a function to run. So this is like saying at most quadratic, whereas this says something about a lower and upper bound, both at most quadratic and at least quadratic time is required. Now, to use this mathematical notation effectively, you have to be quite precise about what you're describing. What is n in relation to the problem? If n is just the input number, then things are simple. But n might be the length of the input sequence, and that means there are lots of sequences all with the same length. So are you describing how long it takes for a length n sequence in the worst case or best case, in average case, across all different sequences of length n? That's something you'd want to specify if you were going to go prove properties about functions. And all that will become important in later courses. But I think in this course, the important thing is to recognize that there are different general patterns of growth in the time it takes for a function to complete. The most common are the 5 that I've shown you here. And when people discuss logarithmic growth, sometimes they don't say logarithmic growth. Instead, they say big theta log n or big O log n.